Let's look at canonical forms for our algebraic Boolean functions. Canonical forms means it's the simplest, most significant standard forms that we have. They're not necessarily simplified. We've looked at simplifying using our Boolean algebra postulates. They're not necessarily simplified, but they're easy to compare. So if we want to compare algebraic functions, it's nice if they have the same form, if we want to compare anything. So they are a unique algebraic signature to the function, and there are two canonical forms. One is a sum of minterms, the other is the product of maxterms. Remember, when we're talking about sum, we mean or, and you'll see this will be the or of anded terms, and product we mean and this is the and of ored terms. So if we consider a binary variable x, in its normal form it's just x, but it also has a complement form x prime. So there's two possibilities there. If we then consider two binary variables, x and y, then we have 2 to the 4, or 4 possible combinations of and terms. We have x prime, x prime y, xy prime, and xy. These are our minterms. These are the standard products, or the minterms, of a two variable combination, two variable term. There's also 2 to the 4, 2 squared, or 4 possible or terms as listed here, x or y prime, x prime or y, x prime or y prime. These are our standard max terms. So the max terms are or terms. Each max term is the complement of the corresponding min term. So if we took the complement of x prime and y prime, we can use De Morgan's theorem, and the complement of that is x or y. That's important, but because we'll see this is x prime, y prime is min term 0, x or y is max term 0. So that's important, and we get to that each min term is a complement of the max term and vice versa, and we can use De Morgan's theorem to determine it. So if we look at our minterm for when x and y are 0, 0, that's minterm x prime, y prime, it's max term x or y. 0, 1, that's x prime, y, and it's max term x or y prime. And you can read the rest. X is 1, y is a 0, that's an xy prime, max term x prime or y. So for our minterms, when x is a 0, we complement the literal. For our max terms, when x is a 1, we complement the literal, or when the variable is a 1, we complement the literal. And we show here that by De Morgan's theorem, x prime, y for minterm 0, the complement of that is max term 0. For minterm 1, the complement of that is max term 1. You can show that for minterm 2 and 3. So again, when x and y are 0, 0, if we evaluate this minterm, that minterm is equal to 1. So the key here is the minterm is equal to 1 according to the binary value of your x, of the combination of x and y. So here when x and y are 1, 1, that's a binary 3. When x, y are both 1, that minterm is equal to a 1. The max term, on the other hand, is equal to a 0. So that's the key here also. They're the dual of each other. So when the minterm is equal to a 1, the max term is equal to a 0. Makes sense? They're the complement of each other. So we use a lowercase m with the subscript to say for the minterm, uppercase m with the subscript for the max term. So we can use these use symbols for this. And then when we want to expand it, we can expand it into, again, this is just for two variables, into its and term product, or its and product term, or its or sum term, respectively. If we have 3 variables, then we have 8 different combinations. So we have 8 minterms and 8 max terms. Again, the minterm, that's our static product term. It's the and of each variable, primed if the variables represent a 0, unprimed if it's representing a 1. For 3 variables, there's 8 max terms. Again, each of the max terms are the complement of the minterm. It's an or of each variable, primed if the variable represents a 1, unprimed if it represents a 0. So again, we can show here that minterm 7, the prime of that is in fact equal to max term 7. So our minterm 7, x, y, z, right? So our minterm 7 prime is x, y, z prime, and then by De Morgan's theorem, x prime or y prime or z prime, and check, that's max term 7. So what we can do is we can very easily make an algebraic expression from a truth table when we're using the min terms or the max terms. So if we want to form an algebraic expression using these min terms, what we do is wherever the function is equal to a 1, we sum those min terms. So f1 then is the sum of, it's equal to a 1 at minterm 1, minterm 4, and minterm 7. So we say it's equal to the sum of minterm 1, minterm 4, and minterm 7. Then we can expand that. We can expand that if we know the and product that represents those min terms. We can also write this in even more of a shorthand notation, and we can say this is just equal to the sum of 1, 4, and 7, and that is a concise representation of that truth table. We do have to know, additionally, however, that just says F1 is 1, 4, and 7. In order for that to become the truth table, we have to know that's equal to F1 of X, Y, and Z. So we know which variable is X, Y, and Z, how many variables we have. If we take the complement, the complement then is the sum of all the min terms where the function is equal to a 0. So we can write that in terms of our symbol for each of the min terms, and then we can expand the min terms into the product terms that they represent in terms of the variables of the function. For product of max terms, then we form an algebraic expression wherever the function is equal to a 0. It's the it's the product of these max terms. I wrote this here as the sum. So let me just correct this real quickly. This should be an and. That should be an and, right? And, because it's the product of max terms. So those products means that should be an and. And then when we expand max term 0, that's x or y or z. And our max term 2 here, because for 2, the y is equal to a 1, so that's our x or y prime or z. So the key here is when it's a max term, we want to pull out the terms where the function is equal to a 0. So if the inputs are, for example, 0, 0, 0, then this max term here will be 0, and it will be ANDed with all the other terms, so the function will be a 0. So that's the idea here, because it's a sum term. So if we want to form an algebraic expression using min terms for each of these, you can go ahead and pause and try it. But we can write this for F2. For F2, it's min terms, right? So for the uncomplemented form of the function, we want to pick the ones, right? So that's equal to the sum of what's that, 3, 5, 6, and 7. So then we want to expand that. So that's equal to its x, y, and z. So our 3 is x prime y z, ORed with 5, which is x y prime z. That's 1, 0, 1. Or 6, which is x y z prime, or 7, which is x y z, right? As long as we know those max terms. If we want to do f2 prime, we just pick the zeros. So we pick the zeros, and we still use the min terms. So it's going to be we'll write it as that's the sum of 0, 1, 2, and 4. So we get our x prime, y prime, z prime, or x prime, y, z, where only z is a 1, or x prime, y is a 1, z prime, or x, y prime, z prime. So we don't have the same terms in either of these in F2 or F2 prime because they're the complement of each other. So this just shows that what we did there. So finding an algebraic expression in the form of the sum of minterms, we just find the function f can be found as the sum of the minterms that result in f equaling 1. So if we want to convert then to a product of max terms, then we can complement a function. So we need f1 prime prime, the double complement, right, gives us that. So if we first find the complement of f1, that's all the minterms that are the sum of all the minterms where the function's equal to a 0. So that's 0, 2, 3, 5, and 6. Then we expand that into their respective product terms, some of those product terms. If we then complement that, we're going to end back the complement. The double complement of the function is the function itself. We can do that then using De Morgan's theorem. We complement that, we get back to f1. We complement that using De Morgan's theorem. Then we take the, you can convert all the dual of the function, convert all the ors to ands and the ands of ors, and complement each literal. And you should verify to yourself and practice this. This is De Morgan's theorem twice, or taking the complement of the function. And we see then that x or y or z, that's max term 0. X or y prime or z, that's max term 2. And here we have max term 3, where just y and z are primed, max term 5, where x and z are primed, and max term 6, where x and y are primed. So what we have is the product term. So if we take the function and find the sum of minterms that represent the complement of the function, and then we complement that again using our De Morgan's theorem, then we end up with our product of max terms. We can also just pull out the product of max terms from the table, but this shows that, in fact, that's the case. So we use this sign for the product. So the product of max terms where the function is equal to 0, then it will also give us a representation of the function in product of max terms form. So why don't you try that same exercise with function 2, f2 here. It's already given on this slide what f2 is in terms of the sum of minterms, 3, 5, 6, and 7, where the function is equal to a 1. f2 prime, 0, 1, 2, and 4, where the function is equal to a 0. And this says, find f2 using the product of max terms, find it directly from the table, and then take the use De Morgan's theorem to take the prime of f2 prime to get back to f2, and that'll give you something in product of max terms form as well.